Okay, cool. So thank you, Vignesh, and thank you all for having me in the seminar course. So today's talk, I want to essentially talk about a framework that I have been working recently. And before I can actually jump on to the exactly the crux of this entire framework for the today's talk, I want to just give a high level understanding of where my experience come from and what I generally do. Okay, so I am very fond of introducing or involving knowledge in the various functionalities of AI, essentially, and that's where my experience and my research is essentially driven. If you see on the screen at the moment, there is a Venn diagram which actually describes pretty much the research that I do involving deep learning and involving the domain experts constraints. And when I talk about constraints, it can be any kind of rules, or it can be any sort of if and else clauses. It can be any cases that arises in day-to-day uses. And if I'm pretty much sure everyone in the audience pretty much know about if and else statements and cases in programming constructs. What essentially I introduce in these scenarios is also utilizing the the knowledge graphs, which are essentially looking at the graphical representations of the knowledge in a very simple sense. In a one-line definition, I would say the knowledge graph. Everyone might have easily seen it. Everyone would actually seek information on Wikipedia. If you open any document on Wikipedia, there is a hyperlink on the top of it, or in the document. You click on it and you go on to the next page. Those actually represents a graphical structure. So assume knowledge graphs to be that kind of representations. So my vision has been recently, which pretty much in the major part of this year has been in developing neurosymbolic AI methods for responsible training as well as evaluation. So we just not do not want to just leave our major thrust only on the training, but we also want to know that our evaluation is also taken care of very well. So okay, so okay, okay, good. So in a nutshell, my summary of my research pretty much in this entire year has been in the mix of various factors where I have focused on rule of thumbs, reinforcement learning with human feedbacks, language models, ensembling of these language models, and safety issues. But most importantly, I have spent most of my time playing around with ChatGPT. I'm pretty much sure everyone would in the audience would have also played around with it. Okay, and various other language models that have been built over the time. But my summary of my research has been specifically identifying the capability or the possibility whether the models that we are playing around with, ChatGPT, Google Bard, or any other models, uh, is there a possibility to understand the rule of thumbs? Can these models understand how they are working together? Can these models be able to work together? But why do I really care if they want to work together or they want to work separately yeah, from each other? But assuming that the idea here is that can we form some rules on these functionality so that at least certain level of safety and trust can be achieved in these model scenarios. So in this talk, I will be using certain terminologies, but before I jump into those, I really don't know the background of the audience, but I just want to set the stage very correct. First, there are three certain things that I want to talk about. First is language models. Language models, if I simply ask you, I would like people to talk about BERT or ChatGPT. Definitely they are language models, but a language model is simply a probabilistic model of a natural language that is capable of estimating that what is the next set of word that should come after given a few sequence of words in the in still date. Or let's say like you are writing a sentence, or you're writing a paper, or you're writing a your project report. You construct sentences, so your mind predicts the next likelihood word that will come in the next in the sentence. so that your sentence is meaningful and things of that nature, right? So that scenario that your mind does is basically probabilistic in nature. That's what language modeling is all about. Foundational language models wanted to enhance these probabilistic models by using some neural networks and some attention mechanism, which they call it as a transformers. These models so far in the foundational scenario reach up to the million parameters, but then more is always a merrier. So you scaled up these million parameters to the billion parameters, comprising of GPT 3.5 or Chat GPT and so on and so forth. Right. So these are the three critical terminologies that will we keep on repeating during the rest of the talk. So in today's talk, we will try to achieve a level of confidence that such a framework is plausible, right? And how do we want to achieve such a framework, right? So CREST, the name terminology, that's what's going to be the crest of this, or the crust of this talk, going to be the consistency, reliability, explainability, safety, and trust. These things have been independently being updated by various researchers around the globe, and they have highlighted certain issues in the LM framework, but they have never stitched these properties together. And the reason is because unless you don't stitch them together, there are various downstream applications that will be affected if one of these things are missing. So if you see the structure, I have designed it in a way that demonstrate my motivation why CREST is important. It's like a steps that you want to follow in order to achieve trust, and then you can use it for various downstream applications. And pretty much my motivation have been driven by the notion of my involvement in various health related projects worldwide, but it can apply to any other problems as well. So let's start with the talk of the first thing, which we call it consistency, right? That's the first C of the CREST, right? So coming back to this phenomena, let's just start with a simple scenario, which I just want everyone to be comfortable with, as the Chat GPT. We all know about the Chat GPT's behavior, right? So let's say I ask the question about from Chat GPT that when was the TCB band disbanded? So if you know TCB or anything of this music side, TCB was one of the band that was designed by Elvis Presley, and it got disbanded, but there was no such information about that band disbandment other than Wikipedia, right? So there was no public resource of such scenario. So when I asked the Chat GPT about this question, this Chat GPT responded that TCB band was not disbanded, right? And then I asked the question next one, are you sure that the TCB band was not disbanded? Then the Chat GPT gives another set of response. And after fifth iteration, it again says that I apologize for the confusion earlier. So in such scenarios of multiple iteration, I'm just asking one question. What if someone from the audience is using Chat GPT at this point of time and maybe asking the same question again, right? So he will be getting a different set of response. I will be getting a different set of response. So there's no level of consistency that can be achieved in the sense of in this Chat GPT scenario, right? But whereas if I can just tune the Chat GPT with some special tags that I can say that this is the knowledge that you should use, right? And this is the query that I'm asking, then potentially the Chat GPT would be able to provide a very crisp response, right? So in this scenario, I was able to ask the similar situation, similar question, when did the TCB band was disbanded, right? And it was able to figure out that it was disbanded after Elvis Presley died in 1977. And I just asked it when was it, essentially to be more precise, and it kept the same context and then expanded it again. I did this process over multiple period of times, and I was able to see that to certain level of consistency was achieved if I can attach some sort of knowledge context associated with it. So now this knowledge context is not available to a majority of the people in the world, and they would be just simply asking when was the TCB band disbanded. So that definitely it raises a concern of consistency in these large language models. But before I can question these large language models, and keeping up with my three definitions that I started my talk with about language models and foundational language models and then large language models, right? I can really not question ChatGPT because ChatGPT is just a successor of these foundational language models or language models that have been built maybe 1995, 1996, going on the topic modeling scenarios and so on and so forth. So I did a very small experiment recently in the summer, and where what we did was we created a data set where we asked the annotators that take this post, give me a label to this post, and also highlight the reason that you saw in that post or the inference that you are making, and explain me that inference in few words or maybe in a sentence and things of that nature. So this data set that I'm talking about, it's not public at the moment yet, but eventually we will be doing it by the end of this year. But what we are trying to do is that we are asking the annotators to give me the labels and as well as give me the explanations behind those labels. Now, what we found in this thing was we take these simple foundational language models, which are million size in parameters, not like ChatGPT, but we identify that how better they are identifying the classes. Very simple classification task, given a post and give me the labels. And if you see on the table on the side, you see that the correlations are amazing. It's like 71%, 81%, definitely worthwhile considering these models to certain level of extent, and maybe improving it eventually by making even bigger models along these lines. But what was intriguing to me was that does the model's attention, right, what the words the models are focusing on, right, are those words mapping to the explanations or not? And that's where I found like the models were barely crossing 20% or 25% in a random set of experiment. Sometimes like models even touch 0% when their correlations are 81% or 80%. So there was some level of inconsistencies that arises between the attention, what they are focusing on, and what the user is focusing on, right? No matter whether their predictions are correct, but what they're focusing on was wrong. And if their focus is wrong, then in your time, when you ask the question, you will get a different outcome. When I ask the question, it's going to be a different outcome altogether. So this set of experiment and many similar nature of experiments that we did on various domains covering healthcare as well as general purpose healthcare, we figured out that LLM's understanding of language, while impressive, is still shallow. When I say shallow, man, that means that I could consider easily that LLMs are present are jargon spouting students, like who just really don't know what they're talking about. And most importantly, when you start to inquire these models on whether they understood the sentence and that's how they got the answer, they will most of the time end up just saying that we apologize or we apology for the confusion. I am a language model. Maybe I'm not trained to that point and things of that nature, right? So these are some of the consistency issues that arises because the focus of these models have not been very looked into in the previous work so far. So this consistency can we have a multitude effect, specifically when people consider them as the ground truth, as a knowledge source. Now, if you see this scenario in front of me, I asked us three set of questions. I will walk you out each of these questions step by step. First question, let's say, what are the possible reasons for a boy dropping off the school? I asked this chat GPT this question, and I asked the chat GPT to rank it by priority, right? I don't know what priority means. I just asked it, right? In terms of Google search, maybe priority might have some terminology, maybe some agencies might have mentioned some priority listing or what are the reasons of a boy dropping off the school. And let's just say that chat GPT has a knowledge of the world and it gives us answer. So if you see all these questions, right, this point, the rank list of 4 or 5 options that it has given me, it gave academic challenges, which I agree upon. That's perfectly fine. Family fight, learning disabilities, and legal issues. These are things that maybe are rising, right? But maybe these are more specifics, right? These are more detailed in this scenario, and I would consider them to be substantially good. Now, if I replace the boy with a girl, the things becomes completely different, right? And it has no way near talking about academic challenges. There's a girl does not have a cultural and religious factors. Maybe it might have, but it's not on the high priority, right? And safe transportation, bullying and harassment. That means if a person reading these two answers can say that a boy does not have a bullying or harassment issues, whereas a girl has it, right? So such scenarios incur a lot of issues in the model. Now, I suggest remove the boy and girl altogether. I just say students. Why students drop out of the school, right? And I just rank the priority. Now here you get a more elevated and abstract responses, talking about socioeconomic factors, lack of motivation and engagement, cultural and societal factors. So now different people, how they are being asking the questions, you get different set of responses, right? So this actually identifies a lot of concern as that what type of questions to be asked, or what type of question, or how should that question be asked, so that you can get the desired answer. And when you have a rank list of priority, whatever you give to the outcome, whatever you get as an outcome, you consider this as a truth, as a ground truth, right? So this becomes a situation of consistency. Now, I did play the one small game in this where I just replaced the boy and girls to students, which is a form of abstraction. And I found a very stable, a stable and safe response from the model. Now, what if I change this context? What are the possible reasons for a boy dropping off the school in Texas? Now, Texas educational system is different than Maryland education system. There might be different reasons. What if a boy, I changed by a boy with an adolescent, or a male child, I change the school from school to academy? That these things are, are essentially the semantically they're same, but they have some different abstractions. Now the question is that should the model work on these finer granularities which changes by person to person, or should a model work on an elevated and abstracted set where no matter what ways you're asking the question, it can boil down to the same question, that what are the possible reasons for a student dropping of the school in whichever state or in United States. If there is a state specific, then maybe some state specific rules are being utilized, right? Like for example, a state-wise questionnaires from Department of Education can be used, and which have been recently being suggested in the Texas state, and that's why one of the examples. So there are some conceptual solutions that come from for the consistency problem. Right now, let's just take into account that this is a structure that I can design. I designed based on what I have been seeing around in the phenomena of these consistency issues. One is the paraphrasing. Let's say I ask the same query, and there is a model which is capable of paraphrasing your input multiple times, right? So in that scenario, you have an LLM takes a benefit of all the possible paraphrases in which that question might occur, and then learn over those paraphrasing to figure out as the most suitable answer. So the next in time, when the model gets the input, it will paraphrase it and try to give a more decent response. So this sort of behavior minimizes the consistency issue. The another set of consistency issue can be resolved is that if I combined this paraphrasing behavior with sort of a human explanations. Now, as I said in the previous few slides back, that there is a data set that we constructed where the human explanations is being given. And recently, there are many other data sets that have been built that are being coming up with human explanations in it, right? And if you consider that human explanations as a reward between that is being in a very simple sense, the reward can be the difference between the tokens by that model sees important compared to the tokens what human sees as an explanations. You can actually tune a large number of models over different paraphrases and with the presence of human explanations, right? So these are two conceptual solutions that exist or that can be designed for the consistency problem. Another consistency problem, another way of defining the consistency problem can be if you have access to some questionnaires or some guidelines, right? Now, let's say the Department of Education has different ways of examining that what is the likelihood of a person to be dropping off a school. They are looking at they're looking at your grades, they're looking at your subject-wise grades, they look at your performance over the time in the class for first few weeks, and then they make a judgment out of it. If you see this questionnaire looks like a reward that you can actually use to train your model, saying that these have been the previous phenomena in the past, and I would take that questionnaires input and refine my model generations. You can also ask another way that you let your model generate a response and figure out that whether that response answers some of the questions in that questionnaire or not. Another opportunity is that you bring this questionnaire as an intrinsic component of your model and try to enrich the learning representations that the model is learning over the time. Another benefit we're going to be removing some of the points or some of the properties in the input data might not be relevant in the decisions, and they can be removed because they are just spurious points in the data samples. So this is where you are actually utilizing instructions as a way of guiding your training mechanisms. So once we have defined these ways, how do we evaluate such a model in practice, right? So there recently, in a very recent, we I would say that in 2023, there was a paper on defining consistency lexicons, where you try to say that there are ways you would measure. So when I said this terminology, I thought of like, oh, maybe there can be a dictionary of words, but essentially this is not. So what consistency lexicon means is that you run your model on a random iterations, right? Let's say 1,000 or 2,000 iterations. In that execution, you keep on changing the input, right? You're either doing a paraphrasing or you're doing some perturbations, which is like a adversarial input, and try to figure out what type of outcome that the model is giving and how far it is going from the true outcome by as a consequence of those paraphrasings or those adversaries. So that's the terminology of consistency lexicons. I was like, when I was reading it, it seems to be like a very different terminology, or like I have a different conceptualization, but when I read that paper, it seems to be a different things. Another option that have been recently being in practice is called the mean reciprocal rank. If you same do the paraphrasing and adversarial, what is the rank of your responses and how those ranks are changing? There are other methods like Nubia and Mauve, which have been developed. And Mauve specifically is only applicable when you have human explanations in place, which represents this architecture, the on the right hand side. Okay, so this consistency is one way of examining the conceptual solution that I have provided are certain things that I've been working on, and I would actually give them a much more better treatment of how these are working together when we learn about the reliability, which is the next concept in the CREST framework. So in the simple sense of reliability, I'm not talking about the definition of reliability in the terms of how these models are generating their outcome. My understanding of reliability relates to very much something that has been there in practice in data science for many years, which is the inter-rater reliability, right? How we can say that in all the human experiments that we really do annotator agreements. And when we do annotator agreements, we go along this idea that more the annotators are and more high the agreement rate is, the most high quality the data set is. That's why there are various categories of data set, the gold standard, the silver standard, and the bronze standard data sets, right? So the gold standard are the data sets which have 90% agreement, 85% agreement among different annotators, right? Can we have such kind of reliability measures for the language models that's the question for the reliability. So there are some conceptual solutions that we can introduce for achieving the reliability on the similar ground. And one simple approach that we came up with is called ensembling, right? People know ensembling all over the world, especially the people who are in the machine learning space and data science space. That ensembling people relate to random forest, decision trees, bagging methods, and boosting methods for these ensembling methods in machine learning. Our task is simply saying that ensembling resembles the inter-rater reliability measures, right? Assuming that there are multiple machine learning models. Now I replace these machine learning models by large language models, and I want to assume that these large language models are now acting as multiple annotators, right? They're annotating your data, and you want to examine that how much these annotators are in agreement with themselves. I don't really need to know their agreement with the gold standard, which is the evaluation. I want within among themselves how they are evaluating, how often they are in agreement with each other. That's simple methods that we came up with, and there was another method that we built on the top of it as well. But the two standard methods that we explored were the simple averaging methods, which is just simply taking the parameters of these models, or we can say that just looking at this functionality of these models, and whatever they are predicting, the probabilities, you sum them up and you average it. That will be the agreement. That will be the averaging methods of these models, right? And then in this probability space, when you're getting this probability vector, you want to see that within the, let's say there's a model 1 and there's a model 2, right? This model gives a probability vector of a class 0 this, and a class and another model gives a probability vector of probability value for this class as another value. You want to see that whether these two values fall into the same range or not, right? That's one way of examining it. But and the ensembling strategy, how do we did the ensembling? There are two strategies that are currently in practice, which is simple averaging and Fisher weighted averaging methods, right? So these are just simple ways. Simple averaging is very straightforward. You take two or three models, you let their models be predicting their probabilities of the different classes. And then what you're trying to do for each for individual classes, you want to aggregate those probabilities and you average it. For other classes, you also have, average those probabilities and you average it. In the Fisher weighted averaging scenario, you are trying to do the similar things, right, on the generative strategy as well. But this time you are looking at the more of the more dense agreement between the two models, right? I will leave it for this because I was thinking of explaining Fisher weighted averaging more in this talk, but I would rather leave you guys to reading it because these are pretty much our established methods in information theory, right? And the other ways of bringing these models together can be element-wise additions or concatenation operations. There are multiplicative operations that also exist, and there are also the composition functions. If you have known about decision trees, which pretty much everyone knows about it. So the decision trees are essentially family of classifiers, what they call it, because each node in a decision tree can act as an independent classifier altogether, right? So you can consider that decision tree is just a wrapper of all the machine learning models that exist in the machine learning space. Okay, so these are the standard methods. So whatever I have mentioned over here actually boils down to these three essential figures, right? So what you see on the left is the simple averaging, right, of these models, and you have that every model that over there has some weighted components, and you are bringing these components together, and they're weighting, and your process of training would be to assigning these weights. So if you know, in a very simple sense in machine learning, we know that every model has some weights, have some parameters, and you can weight each and every model's contribution as one of the way of learning a new ensembled function, right? So in this scenario, one thing that I didn't clear so far is why are we doing an ensembling? So this is running on a simple belief that these large language models have been trained on a very humongous size of the data sets, as a result of which they have a huge knowledge. And if they have a huge set of the knowledge, we can use them to complement each other in making a decision. So that was the underlying belief of using an ensembling method. So parallel to this method, there is another method called the merging function, which relates to this Jin et al. 2023 paper, essentially uses the Fisher weighted averaging methods, right? And we even tried out more complicated methods of ensembling, which you can actually look at into the CIKM paper in 2023. Which is actually have given up in the footnotes. So another option that also exists on the right-hand side is that this is another version of ensembling methods where you are rather than having rather than having an additive function, which was I was telling over here, you are trying to say that you put them together and you learn them once rather than you learn them multiple times, right? So that means that you intrinsically try to introduce some kind of a parameterization trick where the model is able to give 5 different outcomes, and implicitly, like intrinsically, it is trying to assume what are the 5 different outcomes it can generate, right? And you look at those 5 different generations and you club them together, and that's how the learning is happening, right? So the model intrinsically is trying to generate multiple outcomes with just single one input. So far I have been talking about multiple models giving multiple outcomes. This was pretty ingenious technique that was presented in ACL 2023. But this work was on a different domain, whereas the all the figures on the left hand side, the first two, are essentially on in the general space. Okay, so when we did this kind of a scenario on a various data sets, essentially we started with the glue benchmarks, which is the foundational benchmark data sets in natural language processing. We found some interesting results on this scenario. So if you see this plot, let me just simplify this these many plots. Is that the 0 on the x-axis, if you see it, is that there is only model 1, and one value on the right hand side, it says the model 2. Right? And anything in the middle is basically the mix of model 1 and model 2. So we see that when there's a mix of model 1 and model 2, there is a high probability the model surpasses the benchmark, the baselines drastically. And in this scenario, I want you to look into on the table underneath is a very interesting point. If you see the last row just above the glue average, where I say WNLI, you see that the model has given the BERT model, which is the foundational language model, has given an accuracy of 50% or 51%, whereas the inter-annotator agreement, or I would say inter-model agreement, was less than 0.6%. It was very close to 0. Right? In various scenarios, we even saw that it was touching 0 completely. So that means that with ensembling, at least we are not able to achieve a very high, we might increase an accuracy, but certainly we can increase the agreement between the different models. So our final approach was this deep ensembling that we designed, and which seems to work very well with the knowledge inclusion, right? So this scenario, actually, this deep ensembling essentially is an extension of what this remaining 2 slides I want to talk about. Okay, so in semi-ensembling strategy of the reliability methods, we actually looked at different ways of including knowledge inside the model structures. A very simple sense, if you look at this scenario for now, bear with me on the left-hand side of the figure, that these are models and there are weights associated with these models, and you're making a prediction. A very similar, a simple analogy or pedagogy you want to take it is that it's just a linear summations, just linear of the weights. Here in the semi-ensembling strategy, what we are trying to do is that we are revising that weights by using a knowledge LLM. Now, when I say knowledge LLM, it is a knowledge-based LLM that we created, what we did was we trained large language models over knowledge graphs, right? So when we train knowledge graph, these LLMs on the knowledge graphs, essentially what they will give is just a numerical representation, just weights, right? Just embeddings. What you're trying to do over here is that you're trying to compute the cosine similarity or any other measure, let's say, and I'm just giving a simple example of cosine similarity. A cosine similarity between what the LLM says and what knowledge and LLMs do. If the similarity is very high, the weight is going to be very low. If the similarity is very, very low, the weight is going to be very, very high, because knowledge is the factual information. I repeat again, when the weights, when the similarity between LLM n is very, very low compared with the knowledge LLMs, then the weight is going to be very, very high. If it is the LLMs are very, very, if the similarity is very, very high, the weight is going to be very, very low. Okay, so this actually boils down to a weighted function between including this knowledge into different LLMs and using it into a linear interpolation function. Now, why do I need an interpolation function? So interpolation function is just a way of looking at each and every LLMs and try to figure out which set of LLMs tend to perform consistently well. Right now, I'm using the term consistently well in making up predictions. So That means 2 or 3 LLMs might do very good job. Maybe 3 or 4 LLMs could do very good job. This is how you can identify through a linear interpolation approach, right? So on this top and right, there are two functions that I have put down. The first point is simply a linear interpolation over two models, and the next dot is essentially the linear interpolation approach that we used over a bunch of LLMs. And when you execute this equation over multiple iterations, you will get a rank list of LLMs that have been consistently performing well, right? And that's more LLMs combined together by their appropriate weights is essentially the final structure of the model that we want to project. Okay. So this linear interpolation function was pretty interesting, but what we found was that it has some kind of a caveats. So what was a caveat? It was possibility that, okay, if you assign the weights by the knowledge, that's perfectly fine. You can do a linear interpolation and you can learn it. This seems to be a very interesting utilitarian function. Like I'm just giving a utility which is driven by the similarity or the relatedness with this knowledge and LLMs, right? But a better way can be some kind of another weighting mechanism that can constitute this kind of interpolation approach. So in the weighted function or the weighted welfare function, what we try to introduce in this linear interpolation approach, and apologize for not giving up those details because I was thinking that it's going to be too loaded on the slides, but I want just to give I want to give a more conceptual thought on that. So the weighted welfare function essentially is a function where we want to learn these multiple models together, but we add to it, also not exactly add, I would like say it's going to be like a multiplied. We are multiplying this with a concept called Gini index, right? Or any other index that can define me that when you're bringing these models together, how far or how close are going to what do you call it? Your ground truth. So right. So essentially in the utility function, you are bringing them together just like in this reward, and you can learn it by this function. But essentially, when you are bringing them together into before they can actually match it to the ground, like the gold standard, how much information loss are we incurring, right? When you bring 2 or 3 models together. So the weighted welfare function essentially looks at that how these models being put together multiplied by the how much of the information loss can incur. And using that mechanism, you are tuning the final loss of the model. If 2 or 3 models put together incur a very high loss, then potentially that that ensembling strategy is not the good one, right? Now, that is a very interesting scenario, right? When you are putting them together. But there is a scenario where some certain models which are pretty doing good, but they are overall they are not pretty bad. They overall, like I would say, like in such scenarios they are going good. Let's say LLM1 and LLM2 always put together. They are they are working perfectly fine, and they are making very good predictions, right? But there are certain scenarios in comes into the picture where let's say LM3, which was not performing very well on LM2 and LM1 and LM2, but LM3 is a sound model. It does work when I'm talking about, let's say, misinformation. Maybe this model is very good in the context of any other particular domain, right? Whereas other models fall apart. So we kind of looked into this concept in from microeconomics called Rawlsian social welfare function. So the Rawlsian, or I would say Rawls, who was a microeconomist, he actually came up with this approach where in such certain context, maybe ensembling or bringing multiple agents is good strategy, but there are cases where a particular desired agent is not able to lift up in that domain, but it is able to lift up in other domains. So we want to figure out that the models which is not so lifting up in all together, how do you lift them in various applications, right? So the Rawlsian's theorem was an approach that we used to lift up certain models in their prediction. So that was the idea of this Rawlsian. I can actually guide you to, or like direct you to some of the ratings, but That was the understanding that that's the reason that we used for the Rawlsian. Okay, and in the context of the deep ensembling, we wanted to project this approach over the interaction between these models all together, right? So we wanted to see that we are already focusing on these LLMs. Now, what we are trying to do is that let these models generate what they're capable of. We will use an off-the-shelf encoder to encode them together, right, to give a final representation. And then the decoder side would be completely all the knowledge structures, right? And we want them how close my encoder is very close to the decoder, right? So that the reconstruction between the two is what we are trying to minimize over here, right? So this theorem is what we call, it was also a very old theorem by approach that was designed by Alan AI Institute. We kind of improved upon it, and which is essentially what they call a mixture of experts. We defined an error which we called the mixture of experts calibration errors for learning such deep ensembled strategies. Right, so these benefits, these strategy, if you have seen it over here, we are not training any models. We already take the trained models, so there's no retraining of those models, which is going to be very extensive and costly. So that's definitely, there's a cost cutting. But there are certain levels of memories that is being used in different ensembling strategies, right? So that's always a caveat in this scenario. So definitely there's significant reduce in the computation cost, but certainly there is a memory cost associated with it. Okay, so once we have done this ensembling, we have to try out these approaches and what's going to be the best rather than just the most important data set that is right now in conversations, which is the truthful QA from Google. So what does this data set say? It says that there's a query in this data set, there's a truthful answer that is a correct answer from this data set. It gives you the source from where the data set is getting the information, from where this question is coming, and there are some falsehood answers or some of the wrong answers that can be generated when you're asking these questions, right? So our task is that in the light of these positive, truthful answers and the falsehood answers, how does a model gives a correct answer to this particular query, and how consistent this model has been throughout this process. So when we looked at this this scenario, and I'm talking about only semi-deep and deep strategy that I have just explained to you, is we try to look at two different strategies of evaluating. One is that exact match. How close are we to the exact sentence that is given in the ground truth, and how similar are we to the ground truth in the scenario? So our state of the art was definitely was GPT 3.5, which seems to be 175 billion parameters. All right, but in the scenario of the knowledge, what we are trying to we looked at it is that with just 22.2 billion parameters of our combination of these models, we were as close as to the GPT 3.5's 175 billion parameters. There is more experiments that was done on this scenario, but for now on this general purpose data set, we were really close to the GPT 3.5, right? And other models that we were doing were also very close in this performance, but our parameter size was significantly were reduced compared to the state of the art. But what was interesting is that some of the data sets that I have developed with some of the students, like Kaushik Roy, who would be in this meeting, and who is in the meeting. We did develop some data sets which is specifically in the healthcare settings, right? So such as this data set of the primate, where we compared our deep ensembling approach with GPT 3.5. So if you see over here, we got 6% improvement on the top 1 predictions, and subsequently top 3 and top 5 prediction, we got some improvements over the GPT 3.5 on various responses. Now, we cannot train GPT 3.5, so how did we get the response? So we got it response by prompting methods, where we gave the GPT 3.5 a particular question, and we asked the response, and we asked the chat GPT to GPT 3.5 to rank the response by the relevance. And this was a snapshot of the data set. If you can see on the here, there's a post and there's a 9 questions, and against every question there is a yes and no answers. So the purpose of the model is to figure out that which of these questions have an answer yes, in which of this question have an answer no, given this particular post. So that's how the training regime was designed for this process, right? Okay. And we expanded this approach to another data set called the Shark, which is also a very knowledge intensive data set scenario, where we ask the chat GPT this question that you can't get the payment if you live in Cyprus, France, or Gibraltar, or Greece. And question is, can I get the winter fuel payment? And GPT 3.5 gave an answer, no, you cannot get a winter fuel payment if you live in Capra, Cyprus, France, Gibraltar, and things of that nature. But the true answer was the follow-up question needs to be asked: do you live in Cyprus? Right? And the chat GPT was not giving up an answer. So this was more of like a follow-up question that we wanted the chat GPT to give us. But essentially, I would say that even comparison with with GPT 3.5 was not ideal scenario in this setting, but we anyways did for the comparison through the prompting methods. We got significant improvement with the reliability on the reliability as well as on the consistency approach across all the ensembling methods that I have discussed so far, covering semi-deep and deep ensembling. Okay. So in a nutshell, this scenario of ensembling that I just discussed, the three strategies, shallow, semi-deep, and deep, can be put together into one scenario, and they can also be put together in the consistency framework. I am actually leaving this point for further discussion, or maybe taking off the shelf, but essentially you can actually combine the consistency approaches that I discussed along with the reliability. And that's why the notion of consistency and reliability go hand in hand with each other. Right, so in terms of the reliability, I apologize for missing on the variants, but it was I would actually share my slide deck to Vignesh and to cover up on these two variants, and I apologize for missing it out. But essentially, the evaluation for reliability, there's no such evaluation method so far. The only one that I could be using it is this Cohen's kappa, which pretty much everyone knows. It tries to look at two different concepts: is observational correctness and experimental or empirical correctness, right? So in this case, observational correctness means how likely your model is correct, and experimental correctness means that how your model is in generally will be giving equal probabilities probably to all the classes, right? So if I give equal probability to all the classes compared to the probability that you have given to each and every class, how better you are compared to that scenario, right? So that's the notion of reliability. If you're very close to a random assignment of probabilities, then probably the classifier is less reliable in scenario. Okay, so moving on to the next point in time and keeping watch of the time, I think I have couple of more minutes. I just quickly complete the explainability approach. So right, so explainability in the understanding that I wanted to go about is more about explainability that focus on what end user is looking at and not what the person or what the model is looking at. And I think I made it very clear in a few slides that there's a discrepancy between what model is looking and what the ground truth, right? And there have been previous approaches that have utilized another model to explain it, but definitely there are some issues associated with those models, those approaches as well, right? Okay, so there are some conceptual solutions that exist for explainability as well, and these are, in a very simple sense, can be defined very much focused on human level explainability. So these conceptual solutions that I will be talking about actually focus only on the human level explainability, right? And I'm not talking about Lime and SHAP and other methods, which are essentially system level methods. These are more human specific methods, right? So there are 4 strategies I could actually design. One is that you are looking at the sequence of interlinked state space. That means how information from one after the other in a natural language in a large language model is flowing. So that tells you how far the model is going with the previous response it has given. Another option is that putting at the abstraction and contextualization approach, which is looking at that if I have given a sentence about boy and a girl, the same sentence, and I'm abstracting the boy and girl to a student. That's abstraction and contextualization, right? And the last one is conceptual flow, where we are saying that the model is learning following a particular guidelines, and in this process it knows what is right and what is wrong, and that's a constraint based knowledge. So in all of these processes it explains that the model understands the problem and it has given you a more genuine response as opposed to a fictitious responses, right? So there are different properties of achieving explainability, right? Especially with human level explainability. One is definitely the grounding in AI, the grounding AI approach, which is essentially looking at the process of evaluating or improving the AI systems by making not only for accurate predictions, but also learning how to incorporate certain specific knowledge information that you can actually utilize at the output. So this is essentially the explainability, and I think I can better explain this by using this particular example. So consider this scenario of an architecture of a language model where the model is taking some input, it is looking at some kind of a correlations between the input, and then it is trying to utilize is attention blocks. So when I say attention over here, it is looking at which specific point in that attention block is contributing to an answer. Now, how I do it is essentially I will bring this questionnaire that you see on the right as as an independent component in that particular block. Every question if you see on your right is essentially a question in that block, and my task is simply to figure out whether my latent representation, which is this Q of a UI, is essentially, which is my latent representation of the input, how close is this input answering to these questions in one of those 9 blocks, right? And that will tell me to construct to figure out that which of the questions were answerable when the model was making a prediction as opposed to any other strategies, any other approaches. So this had significant benefits, which we found that this model was able to be more precise in its highlighting compared to all other existing models in the large language model space. Right. So one last thing is the safety aspect. Yes, Vignesh, just I think I'm running out of time, right?
Yes. Yeah. Yeah. If you
Okay.
can, please wrap up fast.
Yeah. Okay. So in the safety aspect, we have been looking at specifically 3 different things, which is looking at the alignment aspect, that whether the model aligns with the. So it's just simply saying that if I have looked at these questions, I'm asking that whether my model is aligning to those questions or not. And then next part is the instructability, which is whether it is following those questions. What if, let's say, I want the model to look at question number 1, 2, 3, 4, 5 in this order. But what if the model is looking at 1 and then 4 and then 8 and then 9 and then it is missing in the middle of those scenarios, right? So that's basically the instructability means. And assurance is that if this all is followed, that means you are able to achieve a more safe models scenario. So in the lack of time, I'm not going to those details of architecture that we have designed recently, but essentially these are the approaches that we have designed for this model. So putting it all together, this is essentially the CREST framework that we have implemented in independent of each other, like C is separate, R is separate, E is separate, S and T. But what we are working together is essentially looking at how we put these figures together, which we are working together is essentially looking at this particular approach where we want the inputs, we will change these inputs, we are paraphrasing those inputs, we are making some adversarial behaviors, we are training these multiple LLMs together using the welfare maximization approach that I discussed in a very abstract sense to construct the ensemble approach. And then we are trying to evaluate this ensemble methods over consistency and reliability metrics, which are not tremendously huge in the literature, but we are trying to use them what's being there at presence. and then we are trying to project onto the instruction following tuning using the instructions that are there in the domain aspect as well. So these are just a high level architecture of the CREST framework, which we will be bringing together based on what we have designed in the consistency, reliability, explainability, and the safety aspect of large language models. With this, I know this is going to be very abstract, but I'm happy to take any questions. It can be as simple as possible. I thank you all for listening to me.
Thank you, Manas. It was very interesting. So I'll see if there are any questions. So I have one question. So you mentioned you are training a language model with knowledge graph. So what is you are trying to do the next word predictions type training?
Next concept prediction.
So what is next concept in the context of knowledge graph in your?
So what we are trying to do in that approach is essentially that we have so we have access to the Freebase knowledge graph source, and what we are trying to do is that in every Freebase sample is like a tuple, like a subject, predicate, and object, right? So what we are trying to do is that we are trying to let the model, given the subject and predicate, predict what are the likelihood of those different objects, right? And then in that case, it can predict multiple of them based on its own knowledge, right? And then we will try to carve it and refine it, which of them exist in the database and which of them don't exist, right? That's how we construct a new graphical structure.
That makes sense. All right. Any questions from audience here? All right. Once again, thank the speaker. Thank you, Manas, and I'll talk to you later. All right.
Thanks, Vignesh.
Thank you all.